This media was gratuitously produced by Clear Contributions Audio Video. The intellectual property contained within belongs to Dr. Barbara Van Kyken. Clear Contributions. Let's have clarity.
Before reading it is going to be kind of like, I don't even know what we're doing here. So let's see, that's the pre-lab, how to attach everything, and there aren't any pre-lab questions. Okay, so that is heating under reflux. It's experiment 4, and it starts on page 47. Okay, so do you think I remember where we left off? I think that we have finished out chapter 7 with, as far as the concepts go, and that you've forgotten it all. That was our assignment, right? I get through the end of the chapter, you forget it. I think we've all done our job. So I don't remember what we had done, though, and what we hadn't done as far as practice goes. And so I'd like you to tell me, with chapter 7, have we done the practice problem starting on page 19? And I think that I've asked you the same question like 10 times now, but I can't remember. It was a week ago. Starting on page 19 of the chapter 7 workbook. I'd like to practice this for a day or two, and then start in on chapter 8. Chapter 8's the last one we got for this semester. Starting on page 19, how many of these practice problems did we do? Okay, good. I know that we did 1. I don't know if we even did 2, though.
Maybe we've done 3, because I remember that Mercury with the 2.
No, we've done a couple here.
Okay. Tell me where to start.
I think we've done 4, 5. We've done 5 of them.
You guys did 5?
5. Maybe, yeah. 4. 1, 2, 3, 4. 4. I don't think we did 4. 4 it is. 4 or 5. Yeah, 5.
Yeah, 5.
You worked through 5 of them?
Yep.
Okay, great. I'm going to start with 7. Do 7 and 8. Okay, and I wanted to just go back to this because I wanted to refresh your memory, what we're looking at. All right, yeah, we'll start on 7, which is on page 32, unless you've done that one.
We've done 32.
You have?
Oh, wait, yes, we have.
Yeah.
Yeah, we did this one.
We
Wow.
haven't done 30.
Yeah, that's an alkyne. Did you do, and you did 34. You did these for homework, if I remember now.
Yeah.
All right, then I'll find something else for you. Just a minute. Okay, page 50. Page 50 is a review of all of the different reactions, including chapter 6. Since I want to review chapter 7 with you, though, we'll start with C. Okay. So to refresh your memory, You're listing and labeling all the reactants and going by what is the most reactive. Usually it's going to be the pi bond in these chapters, although you do have the circumstance where you might have an incomplete valence shell. That could happen if you had a bromine radical, for instance, or maybe if you're looking at BH3 with a boron. But at any rate, you're reacting a pi bond every time, and so you're going to create an incomplete valence shell in the organic molecule as a result of that pi bond reacting. So you want to figure out where you're going to develop the carbocation or radical, and then you want to figure out what kinds of other things could be used to stabilize the developing carbocation or radical. So in addition to labeling the features with an incomplete valence shell or a strained ring, which is what we got going on in this chapter, or a pi bond, or you also have, if you have a high concentration, the charges, and then you also have things that you're going to cross off because they won't react, for instance, hydrogen or carbon directly attached to oxygen. Now you also have stabilization features that you also want to make note of. And all I'm going to do next semester is add one more thing to the list of stuff you're looking at, and this is like all of the information that you would need to figure out a reaction. So your stabilization features so far are hyperconjugation, or in other words, bond overlap. The more bond overlap you have, then the more stable it's going to be. If there's a non-bonded electron pair on an adjacent atom in the original molecule, if you have non-bonded electron pair on the atom that you're reacting with the pi bond, which would be the electrophile, and then in the next chapter, we're going to do resonance as the other stabilization feature. Okay, so as a reminder, this chapter was where you're looking at an atom that's going to react with a pi bond that has non-bonded electron pairs, and so it reaches over and it shares those electrons with the carbocation and forms a strained ring. Because it does that, then you don't have a complete carbocation, and so you're not going to have a shift or anything like that. So, let's see, that'd be CH2. You're listing and labeling all the reactants. The CH2Cl2 dichloromethane, that is a solvent that's not reactive, so you can cross that off. And so your complete list is that you have the alkene and the halogen. The most reactive feature is the pi bond. You can induce a partial positive and partial negative charge on the chlorine as it approaches the pi bond. Okay, so that's the labels from this first set of labels over here, first set of 6. Now, because you're going to create an incomplete valence shell, the stabilization features label the primary, secondary, tertiary stuff, so you can figure out where the pi bond is taken away from. And you look for any non-bond electron pairs on an atom that's directly attached to what would become the carbocation. There isn't anything. And then you have the non-bonded electron pairs on the atom that you're reacting with, so that would be these over here. So you note that as a stabilization feature. Okay, step 2 is always show how everything goes together using the mechanism arrows, and you're going from electron rich to electron deficient. So you'd go from the pi bond to the chlorine. But wait, we decided that what you're reacting with has non-bonded electrons, so those could be shared with the developing carbocation, so that would be the secondary carbon in this case. Okay, and then the chlorine is going to let go of the other chlorine atom to create a chloride ion, because it's already gaining 2 bonds. That's plenty. All right, so that's step 2. No, I didn't want to cut it. No. Whatever. Oh, forget it. All right, so now draw what you've created. So 1 is list and label, figure out what you're working with. 2, draw the arrows. 3, look for a shift. Yeah, no shift here. I put it right next to tertiary carbon just to make sure that you understood that concept. Okay, now 4, look at what you got there and see how stable that is. Oh my gosh. No, we're not going to deal with that. So if it's still reactive, then figure out what you're going to do about that problem. So you have a strained ring here, and the only thing left from the first step otherwise is the chloride ion. The most reactive feature is the crazy strained ring. With that, you look for something that has a non-bonded electron pair because you want it to form a new bond so it could let go of one of the bonds. And then you're looking for something present in the highest concentration. And since you only have one thing here, then there isn't really anything to look for. So the strained ring drives the reaction. And once again, you're labeling the primary and secondary because you're going to start to develop a carbocation as the chloride adds on. In addition, the secondary has a weaker hold on the bond. Okay. Step 5, show how the reaction happens. As it adds onto the carbon, then the carbon can let go of the chlorine, and that pops the ring open.
Would this be anti-mechanism?
Very good. Okay, now look at that molecule and see if that's crazy reactive still. Yeah, no, it's okay. So then the last step is figure out if you have any chirality centers, and if so, decide on the stereochemistry. How many chirality centers did you create?
1.
Okay, so if you created 1, then that one is going to be a 50-50 proportion of R and S, because in the first step, you could have added to either side of the trigonal planar surface. The carbon next to it that has the methyl group on it is also a chirality center, but you didn't do anything with it as a result of the reaction. So if it started out as R and the priorities around it didn't change, which it didn't, because you started out with this being priority 1 over here, 2, 3, and 4 for the hydrogen. When you do the priorities now, it'll be 1, 2, 3, 4, same priorities, so that means that it still is labeled R.
the priorities change, would it be 50-50 R and S, or would it
No,
be 100% S?
That'd be 100% S, because you didn't do anything to react at that carbon, and so its configuration stays the way that it is, but the way that you describe it might change depending on how you prioritize the groups attached to it.
Okay.
But we still before final, chiralities 1.
Uh-huh.
Why there was no shift?
Or at least for figuring out what the new stereochemistry is that you created. Why is what?
Why there was no shift?
Because there was never a carbocation. You have to have an empty orbital to shift anything over, and you have this fourth bond here, so you don't have a carbocation there. There's no room to shift anything over. Okay. And then just to further refresh your memory, if you create two chirality centers, then the mechanism becomes important. If you have a carbocation or carbon radical, then you have all four possibilities because it's trigonal planar. So you can do two things at each stage. However, if it's syn or anti, use cis, syn, erythro. Cross off nothing or two. All right. I'm going to work one more with you, but I want to do one that has two chirality centers. I think this will be it. G. We'll try one more, and now that you see kind of how you're working through the problems again, give her a try. See if we can blow the cobwebs out.
What is the ethyl compound?
Ethanol. Okay, what is the all ending telling you?
Oh, yeah, I remember that. Okay.
Okay. Bless you.
Wasn't there a chirality center before we started?
No.
No, there's not, right? Because the double bond. Right?
So the double bond makes it the E or Z, and that's labeled as Z for
Okay.
you, but there isn't a chirality center.
Yeah, I was
before things attach.
thinking carbon 3 was one, but I forgot there was a double bond.
Oh, yeah. I see.
Gotcha.
This isn't enough to break that because you see how it goes down. But this is, when you just go to what it has
Looks like most of you are pretty much there. Still catching up. I can at least go through the first part of this here. So the reactive features of the pi bond, partial positives and negatives you could induce on the bromine since it's a large atom. You're crossing off the carbon and hydrogen of ethanol since that's very has a very strong bond there. You have the partial positive and negative charges and a high concentration. The pi bond is the most reactive feature. That's electron deficient. So electron rich. So you're looking for something that's electron deficient. Since we've crossed off the carbons and hydrogens on the ethanol, then those aren't going to react with it. So you're just left with a partial positive on the bromine. Because the bromine has non-bond electron pairs, that's a nice thing to note also, because then you know that you could use those to stabilize the developing carbocation. That's a resource. And as far as your resources go, you're also looking for the bond overlap, the tertiary or secondary. There is no non-bond electron pair on an adjacent atom. We haven't talked about resonance yet. And shifts, by the way, that is a stabilization feature, but I cover that in step 3, so that's why I didn't have that on your original list. But anyway, I digress. So you've got tertiary carbon here, secondary carbon here. So that means that the carbocation is going to start to develop on this tertiary carbon. But because you've got the non-bonded electron pairs, then that means that those can add on to keep total disaster from happening. And then the bond between the two bromine atoms breaks. Okay, so that's what you create. Look for any shifts. You can't have a shift So then look to see how stable that is. Yeah, not. So you've got a strained ring here. You've got to do something with that. Look at what you have left over. You have a bromide ion left over with a negative charge on it, negative formal charge. And then you have the ethanol. Because it's a strained ring and so crazy reactive, the major consideration is, does something have a non-bound electron pair? What's present in the highest concentration? So you do have the bromine has a negative charge on it, but the oxygen, even though it has a partial negative charge on it, still because it's present in a high concentration, that's the important factor. So the thing driving the reaction is a strained ring. That means you're looking for a high concentration. When it adds on, it's important where it adds on. So you want to figure out where the better carbocation is going to start to develop based on hyperconjugation. So, hello. The electron pair adds onto that carbon. Don't let it spook you that I have it drawn straight up. Remember that that's not how it looks in 3 dimensions, so it might be better actually for you to draw it as planar on that carbon if that's going to mess you over otherwise. Okay, so after you show how it reacts, then you show what you created. I'm going to redo this after all that. Okay, and then you can drop off the hydrogen. Are you okay with the process so far? Even after a Thanksgiving break? You're still with me? Oh, good. That is happy. Okay. That looks like that's okay. Pretty good. So now figure out how many chirality centers you created. You have one here because you have a methyl group, an ethyl group, and a ethoxide, and then all that other mess on the other side. You also have a chirality center here because you have the hydrogen, ethyl group, bromine, and then all the other mess that's attached to it. Since you created 2 chirality centers, the mechanism is important. This has a strained ring, so it has to be an anti-mechanism. The halogens and mercury are going to be that. So to figure the stereochemistry, you're going to have to do cis and erythro. Well, you don't have to, but that's the easy way to do it. You started out with a Z configuration, so that doesn't change. The mechanism type isn't syn, it's anti. The syn mechanism is which one? Do you remember?
The syn is when you have from the same sign.
Mm-hmm. And what ingredients are going to have a syn mechanism?
Boron.
Boron, BH3. Okay. So that means you're going to create a pair of 3 enantiomers. Did you get it? Are you getting caught anywhere?
Only on naming the chirality center with the cis anti-3O. I didn't know what each name meant.
Okay. The cis or Z is the alkene stereochemistry that you're starting with. Mm-hmm. The syn or anti is the mechanism stereochemistry in the middle. So if it's mercury or halogen, it's anti. If it's BH3, it's syn.
Okay.
And then the erythro or 3O is the stereochemistry of the product. So it's reactants, mechanism, product.
Okay.
All right, anything else?
And it's 3O because the oxygen and the bromine are on opposite sides of the chain?
Uh-huh.
Okay.
Yep. Okay, so now, just to make sure you don't forget chapter 6, we'll work one more problem and then you get to work, I'll figure out what letters. I'm going to get you started on everything though. We'll work A. just to make sure you didn't forget that. But it's the same process. I think this goes through double A or something. Oh, through you. 1, 2, 3, 4, 5, 6, 7, 8.
We're doing A on what page? 50?
Chapter 9.
16,
No, I
17,
mean, number 9.
20 minus 3 is 18. I'll give you 9 to work then. 1, 2, 3, 4, 5, 6, 7, 8. Did we?
No.
Oh, okay. Never mind. Sorry. No. Stop it.
Wait, H2SO4.
It's just a source for acid. So it's just creating the hydrogen ion that you can add onto some of the methanol molecules.
Oh, okay.
So you might see it as acid, you might see it as H+, you might see it with a particular acid like H2SO4. It's all the same difference. Well, looks like pretty much. Okay, in the first step you got 3 different potential reactants. The pi bond is the most reactive driving the reaction. Since it's electron rich, you're looking for electron deficient. The thing that has electron deficiency that you could react with is the methanol that has the extra hydrogen tagged on there because it has the positive formal charge on the oxygen. So therefore, the bonds are weakened. Because you're going to be reacting the pi bond, you want to know where it's going to create the electron deficiency. So the secondary carbon is the one you're going with. And I'm going to run out of room, so because of the magic of the iPad, I'll have to probably erase some things as I go. But anyway, your stabilization features, the only one that applies is the overlap of the bonds, the tertiary, secondary, primary issue, because you don't have a non-bond electron pair attached to either of those phenolic carbons. That's what that means. You don't have non-bond electron pair in the hydrogen that you're reacting with. You don't know about resonance yet, but you don't have resonance there. Never mind. So you're going to just add the hydrogen on so that you create the carbocation on the secondary, and that's going to create a real carbocation. So you can't do anything about it. Okay, step 3 is look for a shift. Oh, yeah. Oh, look, you got a quaternary right next door. That means that it's gonna do good things if you move a methyl group over, create a tertiary carbocation. Good. Okay, if you move that over, I'm sorry about erasing things and putting stuff in, but I just wrote too big. Anyway, if you move the methyl group over like that, now you've got the carbocation on a tertiary. All right, step 4, look to see if that's okay. No, that's an incomplete valence shell, so figure out what you're doing with that. So you have from the step before, we've pulled a hydrogen off of the one that had an extra hydrogen, and we got a ton of methanol left over, and it doesn't matter too much anyway, because the methanol is present in a high concentration since it's a reactive solvent. So the incomplete valence shell is driving the reaction at this step. Okay, and the thing that it's looking for is electrons. So your source of electrons is over here. Whoops, that was not what I wanted. Because that's present in a high concentration, that's what you'd select anyway. So the electrons go to the aid of the carbocation. You attach it on there. So your final product is going to be a CH3 here, if that helps you picture better where chirality centers are. I'll compress that in. That, and then you have the methanol attached. Since it has positive formal charge, you can drop off the hydrogen. All right, and then that's okay. That's pretty stable. So last thing is figure out chirality centers. You only have one. Ah, shoot. because the one next door to it has 2 methyl groups. So that's the only one, so RNS. If it had 2 chirality centers, then you'd have all 4 possibilities because you had a carbocation intermediate. Are you guys feeling comfortable with this? Are you feeling confident?
No.
I'd rather use the time to cover new material so we're not cramming it all in at the end. So maybe what I'll have you do is work problems, make sure that you're good with this, and then maybe Wednesday we'll start chapter 8, and that will leave us more time next week to just review everything. Okay, so work through M, whatever's left over. No, we'll make it N because we just, no, yeah, M. Up through M, that'll be 9 problems. And that'll leave 9 for the end. All right, so it's the same process every time. Just look at what you got, analyze it every step, and since it's the same process, hopefully it gets boring for you pretty soon here. If it isn't already. It's on pages 50 through 54, or up to 54, the first one on 54. Whatever we haven't worked yet. So I think I counted 9 problems in addition to what we worked.